Okay, we're ready to do the worksheet 3F for Math 4 course. And really, it is one large problem. Um, we have this table that you were given that I have gone ahead and plugged it into a Desmos table. And I've already typed up the linear, the quadratic, the exponential, and the logarithmic. So right now, all we really have to do at the moment is just go see. Um, there's that. And meanwhile, let's see if I can shrink this down here. No. All right, so there's my linear. Now, did I? We're going to have to go back and fill those in. All right, so for the linear, we're going to write, and I believe it was, I don't remember where the worksheet said to round it, but I'm going to round it to 3 decimal places. All right, so this would be 0.178x minus 279.16. I'll come back for my r squareds in a minute. This would be y equals negative, if I'm going to say 0.000, well, I might as well throw in the extra decimal, plus 0.927x minus 1020.47. So that's what that equation is going to look like. Exponential is going to be 0.592 times 1.002 to the x. That means that it is barely creeping up. It is swinging from left to right, going up, but it almost went the other way. If it had dropped below 1 inside that parentheses, then it would be sweeping down from left to right. And then our logarithmic expression is going to be y equals negative 2600.49 plus 811.062 log of x. And so that's what our equations are going to look like. And then if I scoot over here, I can mark my r squared. I know I put r here, but I've decided, just for the sake of consistency, we're going to look at the r squared values. 0.995, 0.9934, my quadratic is 0.9952, and my linear is 0.9948. Now, several of these are really, really close, all right? These two are really close. The logarithmic and the exponential are 0.99 and some change. Actually, the quadratic comes out ahead of everybody, 0.9952, 0.9950. I think I need to add that down here. And then 0.9948. So all three of these came out really, really close. And you had to scroll out really, really far to see the difference between the 3 or 4 equations. All right, the blue one you can see is the exponential. Now, at this point, perhaps a valid question to ask is, which one of these is more expected to happen. You know, if we're talking about as we go further into the future, how will our maximum age change? Uh, you know, if we believe the red line, which is the quadratic, we'll reach a point where we peak and then we start dying younger. And I'm not sure that that is going to be the conclusion that we'll accept. Likewise, with the blue one, it just skyrockets right on out of there. You know, by the time we reach 3000 and 4000 AD, are we really going to live to be a couple of thousand? Well, I don't know. Modern medicine may take us there. But you know, really, it's in these two other lines, the black line, which is linear, and the green line, which is the logarithmic one. And I don't think that this is truly a linear relationship, even though it is really high on the R squared value. But I think it's the logarithmic that we're going to trust more here. And so when we go back to uh, problems like this, where we ask questions like, based on the correlation coefficients and the coefficients of determination, which model seems to do the best, you know, seems to be doing the best here. You know, all the three of them are very, very close. You know, and we could say that the quadratic and exponential and logarithmic are very close. But log seems to be the best fit. I guess that's the way that we need to describe it here. The logarithm seems to be the best fit here. Now, based on your intuition, what do you expect life expectancy to do in the future? I would say increase. But gradually. Which is more in line with the logarithmic. Now, this asks us to zoom out the way that I did. What do you notice about each? Linear predicts a straight line increase, which we didn't really have that to begin with. Quadratic predicts that age expectancy will eventually go down. You know, at one point we're going to start dying younger, according to that model. And I think that we'd like to think that is no. The exponential predicts that age expectancy will skyrocket. The logarithmic predicts a gradual increase. So we really like the log model, you know, so far with the data that we've got. You know, the life expectancy over the different years in the past. Now, we need to go to the residual plots and describe how they fit what's going on. So let's do it that way. And then well, first of all, let's get in tight. Because we're going to have to see when we start doing the residual plots. All right, for instance, there is the way that the linear is going to go. And we see that the linear, you know, it goes up and down and up and down, and it does kind of what we want it to. And so, you know, when we describe it is scattered as it should be. which means we like linear. You know, that would not be a bad choice. Now, let's go back here. And let's shut him off. Let's pick up the next residuals plot, the parabola. And when I look at it, it's going up and down and up and down, and it's going back and forth. So, you know, when we start asking about this one, scattered also. When we look at I'm going to get rid of those, and then I'm going to go find, that's right, there are no residuals with the exponential. Wait a minute, now what happened here? Did I get, oh, I got rid of the table, is what I did. There we go. All right. So I got this back again. Now I need to do that and that. Oh, now I do have a plot for the exponentials. I wondered about that. All right, well, notice that it's going down, then it's going up, then it's going down, then it's going back and forth and back and forth. And so, you know, once again, this one, you know, is scattering back and forth and doing what we would want it to. And so when I go all the way down here and do the logarithmic, I get the same behavior. So right now the residual plots are not helping me, not a darn bit. And part of it is because that all of these, you know, the pattern of best fit for, say, the exponential is a huge curve. And these guys are almost linear. And when that happens, you're going to fit all of the patterns pretty well. And so you're just going to have to look at where the outcome is. You know, where does this, when I zoom out and I look at, you know, where the plot is going, which one is appropriate to the situation? So really, we checked out all of these, and all of these were doing kind of the same thing, which meant that, you know, and sometimes that'll happen. Sometimes that'll happen that your residual plots are just, you know, they're all going to look good. And so it's kind of like, well, that doesn't help any. All right, so now we need to make a series of predictions based on, I tell you what, I'm going to do this with one of them. And then I think I'm not going to sit there and make you watch me go through all, what, 12 of these, no, 16 of these, but I'll do the linear. All right, the linear was 2020, and there goes the oven again. All right, so I want to shut off our residuals. I don't have to look at them anymore. And we're going to go up here. And all right, the first question was 2020. I think I'm just going to go back and forth here. 2020, what was the linear? So 2020 would be right about, actually, I could probably do all four of them. The linear was the black. And that's going to be about 80.4. That's close enough for me. 80.4 for the linear. And the quadratic was the red one. 2020. Oh, up here. Oh, there he is right there. All right, 80.189, we'll call it 80.2. So the quadratic was 80.2. Excuse me. Whoops, that was meant to go here, not over there. All right, exponential prediction. Let's see, exponential is the blue guy in 2020. That's going to be about 80.6, 80.65. So I guess you almost might call it 80.7. So that's going to be the exponential. And then the logarithmic, the one that we said that we trust the most, is going to be the guy in green. At 2020 is going to be 80.354, so we'll call it 80.4. Now, let's stretch this all the way out to the, well, I guess we could do all of the years this way, but I'm not going to make you sit here and watch me do that. You see what I was doing. You do have to be careful, which color which one is. But I'm going to go ahead and fill the rest of this out and pause it while I do. Okay, that is me going through all of those different years and filling out the predictions based on the different curves. I just, scooted along the curve until I found the year and marked whatever was going on. Now it says to go back to the chart and circle the ones that seem unreasonable. Now, I don't know that there's necessarily anything unreasonable in these first two rows, but by the time we get to the year 3000, I don't think we're going to drop back to dying at 57, and I don't think we're going to live to be 875 years either. I find those not reasonable. Now, as far as the year 1800, I'm not sure that that is reasonable, and I almost have a question mark here. I'm not quite ready to circle it, but it makes me kind of want to. Now, I guess that's about all that the ones that seem unreasonable. So we know that the quadratic and the exponential are not really where we want to go with this. And quite honestly, this seems to be not quite so linear. So I'm not sure that we would agree on linear, which leaves us with logarithmic as far as this data is concerned. If we were to pick a model to use for predicting the R squared, the residuals all tell similar stories. It's kind of common sense that ultimately is going to help us make our final decision here. How you're going to summarize your thoughts, I guess you would say, we would expect life expectancy to increase gradually. And that link down at the bottom is actually somebody had put all this together and gone ahead and plugged everything into the Desmos calculator. But I've left it at the end because I felt like it was good practice for you to punch it in for yourself. But this gives you something to compare it against. And so that is 3F worksheet.